that the Hello and welcome to this section of using Kirchhoff's laws with dependent current sources. So I've got a large problem here. It's actually so big that the circuit continues. So this is sort of one circuit here, and it is a monster, I'll tell you that. But don't get so worried about it, because what you'll find out is when we start solving this guy, you kind of inch your way back all the way up to the front, and then you kind of get the answer. So what we have is this circuit here. We've got one source over here, one voltage source. We have two dependent current sources that are given in the course. We've also got the resistors labeled everywhere, and we also have some currents pre-labeled. Here's I sub 1 coming out of the source here. We have I sub 2, which is kind of in the last leg over here in the middle part of the circuit, and that's really all we have right now. We also have V sub 0 over here, and the problem is, if you're given that V naught, which is that voltage way over at the end there, is 5 volts, then what you want to do is find V sub 1, which is this voltage labeled here in this direction, and V sub G, which is the source voltage. So if you've never done this before, you just kind of go into lockup a little bit. I'd like to talk briefly about why the circuit's written this way. What you've really got going on here, to be honest with you, the way this is drawn, is kind of an impractical circuit. When I looked at a circuit like this for the first time in an engineering course, I was like, what are they talking about? This makes no sense. You've got a wire here, but you don't have anything connected here, so how does the current get back to the source? I mean, the current certainly is not coming from this source and then going through this little wire here and then coming back through the same wire. I mean, that doesn't make any sense. You don't have current going through a wire and then coming back through the wire. At least in a DC. For AC current, yeah, you have oscillating current back and forth. We'll talk about alternating current later. But this is all DC. This is a battery here and some other sources. You don't have current going through a circuit and then coming back through the same wire. So at first I was always confused, like, what does this mean when you have segments of circuits connected? What it really and honestly means is it's impractical. You don't build circuits like this really, but what it's basically saying is, look, you have a circuit over here, very simple loop. It's got a voltage source, it's got two resistors, and then as a result of this, we don't know what the voltage is, but there is some current going around here, and that current we call I sub 1. All right, now totally separate from that, you have this middle section, which is almost like a totally separate circuit. The current that's sort of sourced in the circuit is 25 times whatever the value of I1 is. So once you know what I1 is, you know what this current source is doing, and then of course once you have this active current source going on here, then you have currents and voltages everywhere else in the circuit, and then I sub 2 is then defined. Once you know what I sub 2 is, you have a totally separate third part of the circuit that has another dependent current source that's active at the rate of 40 times whatever I sub 2 is, and then once this guy's active, then the rest of the circuit has got current running around. They're connected here really mostly because when you learn a little bit more about voltage, I think I've even talked about this. Voltage is always between 2 points, right? It's like the bottom of this battery, right, is the low side, the low voltage side. The positive part of this battery, if that's a battery, is the high part. You can think of this bottom part being the bottom part of the mountain, and the top part up here being the top part of the mountain, right? So it's always in terms of 2 points. When you go through a voltage rise like that, it's always like going uphill a mountain or downhill from a mountain. So when you have a bunch of different circuits, which is what we really have here, this is like a separate circuit, and this is like a separate circuit, but they're connected physically to the negative terminal of this battery. What you've really done is kind of what we call grounded. You've probably heard of that before. Grounded this circuit. In other words, we have drawn it so that the bottom here, right, the bottom terminal of all of these components are at 0 volts. And it kind of keeps everything on a level playing field. When you have different circuits that are working together, this is common in a cell phone or in any kind of electronic circuit like a video camera or a television or something. You've got lots of circuits, right? You might have a circuit that controls what the picture looks like in a TV, and then you might have another circuit that controls the tuner for the video signal coming in. And then if it has an antenna, you might have a circuit that controls the waves and the amplification of the waves. So you have lots of different little circuits everywhere is what I'm really trying to say. And those circuits really function together and to produce the product or whatever it is that you're trying to build, right? But you have to have all of those circuits working in harmony, even though they're different circuits. Like one guy's a amplifier for something, and another guy's a picture controller, and another guy's a memory or something like that, you have to have them working together. So you need to have them all operating off of the same base voltage. In other words, since voltage is a change in potential, then you want all of those circuits to have as their base voltage, the bottom of their mountain, so to speak, at 0 volts, let's say. And then that way you don't have any discontinuities in the voltage from circuit to circuit to circuit. You want them all to be on that same level playing field. So this is very common in a car, for instance. The electronics in a car, they're all grounded to a common point. In your home, all the wall outlets, they're all grounded to a common point, which is usually outside your house. It's literally nailed into the ground. So the voltage reference of your entire house, 0 volts, is a known quantity for everything. If you don't do that, I'm getting a little ahead of myself, but if you don't have a common voltage reference, right, and you just let everything float around, then you get really big problems, because you might have one circuit over here that its low voltage level may not be 0 volts. Its low voltage level may be something else, and it's floating around. It's not tied to anything. So you can get these dangerous voltage changes between different circuit elements if they're not tied down to a common point. It can actually cause arcing and melting and things like that. If you have a circuit, a very high voltage circuit over here that instead of 0 to 100 volts, maybe it's operating from 500 volts as a base voltage to 600 volts. The difference being still 100 volts, but maybe its base voltage is floated up, so to speak, is what we usually call it, up to a higher level. And then you have a circuit element over here in the same box, in the same physical box as your guy, and then he is operating properly from 0 volts to 100 volts. Well, then you've got two circuit elements, the base voltage of which are different. And so that can actually cause big-time electrical arcing. So I hope that analogy makes sense. We're going to get into this idea a lot more. But the bottom line is, the thing to pull away from it is, the best practice is when you build circuits that are commingled, co-located, part of the same system, but they're separate circuits, right? You really need to make sure that their voltage level for the base, the low voltage of their sources really, are all in the same potential, all 0 volts. So that when you have a battery here and a battery there and a source here and a source there, all of their 0 potentials are in the same place, so that they're all playing nicely and nobody's floating up and nobody's floating down, creating these dangerous potential differences between each other. So that's what is sort of trying to be illustrated here. You've got a circuit here, you've got a circuit here, and you've got a circuit here. These sources are really dependent on what's going on over here, but we've tied their low sides together so that the potential difference between, I should say, the low side of their voltage between each of these circuits really is at the same place. So if you ever see a circuit like that that's got something tied together kind of at the bottom, that's all that's really happening. It doesn't mean, this is what I thought when I first saw this years and years ago, it doesn't mean that you've got current from this source going through this and doing something nuts and coming back. That's not what it means. It means the potentials are held at a common voltage, 0 volts, the same way it's done in your house, the same way it's done in your car, the same way it's done in any electronic device with multiple little circuit elements going on. They have to be designed and tied together to a common ground, really, is what the word is. All right, so that was a lot of talking. It was more of an aside than anything else. But that's the reason this guy is drawn this way. So when you look at a circuit like this on an exam or on a test, you really kind of need to view it as 3 separate circuits. There's a circuit going on here, there's a circuit going on here, and there's a circuit going on here. And of course, these are dependent current sources, so in real life, this would be like a transistor. And this would be like a transistor, but of course we haven't gotten to transistor theory yet, so we call them dependent current sources. So when we're given that 5 volts is known, then let's go ahead and write that, right? Let's go ahead and write that. So let's write 5 volts, just to remind ourselves. And before we actually solve the problem, I want to do some more labeling. So what you have here is the labeling that you were given, but let's do some labeling. This, let's call I sub 10 ohms. Okay, because that's the current going through there. Let's do this as I sub 40 ohms. This we don't need to label because that current's already given to us. We have I sub 2 here, we have this voltage here. Let's go ahead and label this I sub 20. I'll just go I sub 20 like this. This current's already given to us, and I sub 1's already given to us. So we really don't need to label anything else. So we're given that we have 5 volts. We don't know anything about this because we don't know what the source is, but what we do know is we know way on the end here we have 5 volts. So really, we're going to start at the end of the circuit and end up working our way backwards. So we need to look and see what can we find. We know that this is a voltage drop of 5 volts. Plus 5 here, 0 volts here, 5 volt voltage drop across a 10 ohm resistor. We can find I sub 10 immediately is equal to V over R. The voltage is 5 volts, the resistance is 10, so 5 divided by 10, 0.5 amps. That's the current flowing through this guy. All right, now what else can we find? That's the current going through here. We know the voltage drop here, but notice this. This is 5 volts. It's physically connected by a perfect wire to this resistor. So if we know that this is 5 volts, then we also know that this is 5 volts. That's how voltage works. If it's connected, if you have a battery and a bunch of stuff in parallel like this, where they're all connected across the battery, then the 5 volts applies, the potential applies to everything it's connected to. There's no resistor in the way here. This is an absolutely perfect wire. So this voltage drop is exactly the same as the voltage drop across here, so it's 5 volts. They don't tell you that in the problem. You have to know that yourself. So the current going through the 40 ohm resistor is V over R. The voltage is again 5. The resistance is 40. And so when you take 5 divided by 40, you get 0.125 amps. All right? And that's given to us and allowed us to solve for this simply because we know what the measured value of this. We might build a circuit and we just measure that 5 volts and then we find these currents. So what we want to do next is use this knowledge. We know what this current is. We know what this current is. We want to figure out if we can find what I2 is, because let's just do a thought experiment. Let's do a thought experiment here. If we can figure out from this guy what I2 is, then we'll know what this value is. And then using some Kirchhoff laws here, we might be able to find I sub 1, and then once we know that, we'll know what this value is. So we're kind of working backwards. So how do you think we're going to be able to figure out what I sub 2 is? Well, let's write a Kirchhoff current law at top node. And I think you'll see here at this node right here. So what we have is this guy, this current source is flowing out of the node, so it's positive, so it's 40 I sub 2. Now this current is also flowing out of the node, so I'm going to go ahead and just make it explicit, plus I 40. This guy is flowing out of the node because this is current going down, this is current going down, so here we go, I sub 10. So once and that's equal to 0. So once we substitute in for what we know, what we're going to have is 40 I sub 2 plus, we know what the current is in I40, 0.125. We know what the current through the 10 ohm resistor is, 0.5, is equal to 0. And now you see, because of the way it's all constructed, the only variable I don't know is I sub 2, and I can solve for that now. All right? So what I'm going to have is 40 I sub 2 is equal to, you add these together and you move them to the other side of the equal sign, negative 0.625. And then I sub 2, once you divide by the 40, you'll get negative 0.0156 amps. 0.0156 amps. This is the value of I sub 2. I'm going to kind of, let me just kind of circle in red here. It's not the final answer. It's not what we really came to find, but it's very important because once we know what I sub 2 is now. So because of what we were given here, we were actually able to figure out what this current is. Because see, this is tied to this. So this variable I sub 2 is exactly the same as this variable I sub 2. We were given enough information here to find I sub 2. So the next step will be to go on and see what we can figure out for this midsection. So this value of the current is negative. Now what does this really mean? We've talked about this. If you get negative currents, it just means that the direction that you've drawn everything is really backwards. So if you really construct this circuit, I sub 2 is not really going this way. I sub 2 is really flipped around the other way. But that's just something we keep up here. We don't modify our drawings. We don't go up here and try to flip the direction of the arrow because that would be disaster. We've already written equations assuming that the directions are like this. We get negative numbers. It just means that we were backwards on the way we drew it. It doesn't mean we have to go change our drawing there. And what it also means is since I2 is really negative, this current source, since it's 40 times I sub 2, doesn't really point down. It actually points up. See, we didn't know that. That wasn't drawn that way, but it makes sense because this voltage drop was given to us, we know for an absolute fact this current is going down and this current is going down. So when you think about it, it's actually impossible for this current to be also going down, because it would mean that you would have all three currents going out away from this node, and that's physically impossible. You can't have current sourcing out of just a node intersection. Kirchhoff's current law says whatever current comes in must come out. And you can't have a situation where you have current flying out three different directions with no input current. So what this is all really saying from a sanity point of view is I2 is backwards, which really means this is backwards, which really means if we really built this thing, the current's flowing up into this node and then of course branching off. That's what it really means. So always do a sanity check on what you get. So now we know what I sub 2 is. So we want to now turn our attention to the center section here and figure out what this guy is. And there's lots of different ways to do it, but what we want to figure out, or what we know I should say now, we know what the value of this current is. So notice the way this is drawn. V sub 1 is drawn across the 20 ohm resistor, but it's connected physically with a wire to this resistor here. So V1, really the same voltage V1 that's across this resistor is exactly the same voltage that's across this resistor, because they're physically connected with the wire without any resistors or anything in the way. Now, anytime you have two things physically connected with wires like that, they're perfect, the voltage will be the same across them. That's what voltage is, right? Now, if there were a resistor up here, then this would not apply. But since they're connected with the wire, then what we really can figure out, I'm going to draw it here, is that really this voltage across here is also V1. I'm drawing that myself because it's not given to us in the problem, but you deduce it from what you see. So given this, we can use Ohm's law here. We'll use Ohm's law, and that is that V is equal to IR. Let's apply it to this resistor right here, because we know the current I sub 2, right? Let's say V sub 1 is equal to I sub 2 times R. R is 80. And so what this is I sub 2, we just found negative 0.0156 times 80. Notice we stuck the negative in here because this polarity and everything is all given to us and consistent with our drawing, so we don't care that it's really backwards. We just draw it in the direction of the drawing, which is I times R. I times R. I happens to be negative, so we stick a negative in there. And what we get in the end result is V sub 1 is equal to, it's going to be a negative value, negative 1.248 volts. All right, and I'm going to circle this because this is one of the answers we were seeking. Find V sub 1, right? Notice V sub 1 is a negative value. What does that really mean? It really means that this voltage isn't really, if you drew the circuit and you built it, isn't really in this direction. It's really flipped around, where this is positive and this is negative. Why do you think that's the case? The reason it's the case is because this current is not really flowing in this direction. So I don't want to redraw it and clutter things up, but what it's really saying is this current isn't going down, this current's really flowing up. And this voltage is not really like this, it's really positive to negative. So if current were flowing up, it would be positive, negative. So it's all self-consistent. We know that the voltage across a resistor should be in the direction of the current, positive to negative. So if the current were really flowing up, it should be positive to negative. So it makes sense that the voltage we get is backwards from what we draw here. So again, it's another sanity check. All right, so now we know this voltage. Now we want to try to work our way again back to the source and see if we can figure out basically anything else. We need to eventually find I sub 1. The only way we can find I sub 1 is by doing some loop equations over here that involve this guy, or maybe a current equation. Maybe a current equation is better. So we know what this current is because we use Ohm's law. Let's figure out what this current is here, because again, we know this voltage, then we also know this voltage. So let's figure out what I sub 20 is. I sub 20 is equal to V over R. The voltage just happens to be negative, so negative 1.248. The resistance is 20. So when you take negative 1.248 divided by 20, you're going to get negative 0.0624 amps. That's I sub 20. The reason that I want to do that is because My goal is to find I1 so I can link it back. Let's write a Kirchhoff current law right there. So what I'm going to have is this current is coming out of this node, so it's positive, so it's 25 I sub 1. This current, I sub 20, is flowing out, but I just found that, right? So it's going to be plus negative 0.0624. Notice I put a plus sign here because it's flowing away from the node, but the actual current's negative, so this is how I keep track of it. It's plus because of my sign convention. I plug in the actual value of the current. I sub 2 also flows out, so it's a plus, and I get a negative value for I sub 2 from over here, negative 0.0156, and that's all equal to 0. That's Kirchhoff current law at that node. All right? So whenever you do that, then what you're going to get is 25 I sub 1, and then when you have a negative number here and you add it to a negative number there, you're going to get another negative number, 0.078 is equal to 0. So let's scoot this over. 25 I sub 1 is equal to 0.078. Divide by the 25. What we'll have is I sub 1 is equal to 0.00312 amps. And again, this is not any kind of final answer, but it's an important answer. So I'm going to kind of circle it, kind of keep it in my paper. So I've basically found I sub 1. Now, what does that let me do? Now I know what I sub 1 is. I know what this value of this current is. And it's very simple now to calculate the source voltage once I know what this current is. And that's what we're going to do next. So to do that, we're going to write a Kirchhoff voltage law loop that goes around this way. And we're going to start right underneath this source. So we're going from here up. So we're going from negative to positive. So it's a negative sign here. And I'm going to switch over to this board to do it. So I'm going to do KVL over here. So it's going to be negative VG because we went from negative up to positive. Now, when we go this direction, we're going to go in the positive direction because we're going in the direction of current, IR. So what we're going to have is plus I1 times 60. And then we're going to go I1 times 260 in a positive sense. So let me write I1 times 260, and that's equal to 0. Notice I don't put numbers in here right away. I like to write my equations in terms of variables, so if I screw something up, which is inevitable, I can go back here and say, okay, this is the equation. I plugged in the right value. If I just start writing numbers everywhere, then I get lost. So here what I'm going to have is negative VG plus I1 is given to us. We just found it, 0.00312. So we'll have 0.00312 times 60 plus 0.00312 times 260 is equal to 0. We'll switch colors to break it up a little bit. Negative VG. Now what do you get here? When you take this times 60 and this times 260, multiply and you add them together, what you're going to get is 0.9984, and that's equal to 0. And so when you move this guy over to the other side, it's going to be negative, and then you divide by this negative, you'll get a positive. VG is equal to 0.9984. And then when you look back at all the rounding and the decimals we've done everywhere, you realize that this is pretty darn close to 1 volt, which is really the answer that we're seeking here. This is the final answer. So there you go. What we have found from this guy is the source voltage is actually just a 1 volt source, and the voltage across these resistors here, which was the other thing we were trying to find, is given by this. So let's go through it really quickly. We have this situation where we almost have like 3 separate circuits. They have a common ground, which just means the common reference for the bottom of their voltage is a common point. Because don't forget, this is a current source, but there's a voltage across it, right? There's a voltage across this guy. All this is doing at the bottom is ensuring that the bottom of all of these voltages for these sources are the same physical potential. So you don't have any floating potentials, and anybody here that's operating higher and anybody here is operating lower, creating dangerous voltage drops between your circuit elements. So that's what this is really doing. So we knew this was 5 volts. We calculated the current through it. We also know because it's physically connected here, this is also 5 volts. So we calculate the current through it. Then we do a current law up here and sum the currents going in and out, and we figure out that I sub 2 was able to be solved for because it's the only variable, and it happened to be negative. But we don't let that stress us out. we just keep our drawing exactly as we are, and anytime we need to substitute for I sub 2, we just stick a negative value in there. So next thing we did is we came over here. We know what I sub 2 is. So we calculated the current going through there. Or, I'm sorry, we already knew the current. We knew I sub 2. What we did was we calculated the voltage through here by going I times R. V is equal to I times R. And what we found out is that this V1, which is the same because they're physically connected here in parallel, is equal to, again, it's a negative value. The reason we got negatives everywhere is because everything's flipped around. We talked about that briefly. So once we have V sub 1 here and here, we know this current. Once we know V1 here, we can calculate this current. So we calculate the current through the 20 ohm resistor, again getting a negative value. That's just because the polarity of the voltage is backwards. And then we write a Kirchhoff current law here. The current coming out from the source is here, and then the rest of these guys, we write it in the positive sense because they're coming out, but then when we actually plug in the values of the current, we stick in their true negative values. And then we add them together, we find out what I sub 1 is. So now we know, because of this, we know what the value of I sub 1 is, so this is a very simple circuit. We just write a Kirchhoff voltage law. This is going to be negative because we're going in this direction. This would be a positive voltage drop. This would be a positive voltage drop. We know what the value of I sub 1 is because we calculated that. So we plug in the value of I sub 1, we have our voltage drops, and we solve for the value of the source voltage, which is so close to 1 volt, you might as well say it's basically 1 volt. So this is an excellent problem for 2 reasons. Number 1, it shows you a crazy looking problem with these dependent sources, and they're kind of separated, but they're tied by a common ground. I tried to give you a little explanation to show you what that really means. If it's the first time you've seen one of these, you might still be scratching your head, but hopefully I try to illustrate to you that it's not really that these are connected and there's current coming here and back through and flowing back to the source like that. It's more of separate circuits that are operating independent, more or less, but they're still dependent on other parts of the circuit, much like a transistor amplifier might depend upon current from somewhere else. But their base voltages and their operating voltages, the low part of those potentials, are tied together. It's called common ground. We talked about that, and that's important. There's a whole theory and discussion we could have on that, but just suffice to say that you really should always do that when you're designing complicated circuits because it prevents other issues from cropping up. All right. The other thing that was interesting about this guy was that once we knew the end, which this is what was given to us, we kind of worked backwards. So in a way, this kind of problem has more steps, but it's a little easier than just getting a circuit and writing a ton of Kirchhoff voltage laws and a ton of Kirchhoff current laws and using a matrix to solve for it. We've done those kinds of problems before. This, in my opinion, is a little easier. You find this, then you find that, and you find this, and you find... It's kind of like this thing's connected to this thing, and this thing's connected to this thing, and you can just sort of work your way backwards. So just do yourself a favor and do good labeling. I sub 10 helps me figure out that that's this current. I sub 40 helps me here, and just kind of keeping it all in, keeping track of it all is a challenge. But do yourself a favor and take it slow. The final thing I want to leave you with is something I've mentioned 4 or 5 times. When you realize that you have a negative current or a negative voltage that you've calculated, don't change your game plan. Continue to write your equations in the directions of the current that you've drawn on your paper, and then when you need to plug in for a value, you stick a negative in there. Resist the temptation. An excellent example is this spot right here. You know, a lot of people when they're new, they try to write a Kirchhoff current law here, and they're like, okay, well, this current, I've drawn it this way, but it's really negative, it's really coming in. So they'll try to flip around their sign convention in the middle of the problem. And if you do it right, you know, you might escape unscathed. But what's probably going to happen is you're going to get confused and you're going to be off by a sign somewhere. And then you might as well just trash your paper and throw it in the trash can because it's worthless. If you don't get the right sign here, then you're going to get the wrong value for I1, and then you're going to get the wrong value for this, and your teacher's not going to give you much sympathy. So write your sign conventions in the way that once you have them, and when you plug in the values, then if it's negative, then you put it in parentheses and make it negative, and then you handle the algebra. It may take an extra few lines, but trust me, it'll save you time in the long run. So make sure you know how to do this problem and practice it yourself, and move on with me to the next few sections where we're going to start talking more detail about series and parallel resistors and how we can use the rules of those guys to help us solve more circuits.